standby generator powering a 480/277-volt 4-wire system experienced issues, specifically flickering lights and electronic ballast failures on a single circuit after a transfer switch connected to emergency power. The initial checks of the generator lugs indicated proper voltage and a 60 Hz frequency. The standby generator's ground was connected to a metal junction box where the existing generator was connected, raising concerns about the grounding configuration. Possible causes include incorrect wiring at the junction box, voltage spikes during generator startup, and poor voltage regulation. The ground connection from the standby generator should be connected to the grounding electrode system, not the metal junction box. Starting a large generator can create a voltage spike, which could damage sensitive electronic components like ballasts. Even if the voltage at the generator lugs was initially acceptable, it may have become unstable during the transfer to emergency power. To address these potential issues, first, verify the wiring at the junction box. Ensure the ground connection from the standby generator is connected to the grounding electrode system. Secondly, check the generator's voltage regulator to ensure it's functioning correctly. Thirdly, monitor the voltage at the junction box during the transfer to emergency power to identify any voltage spikes or fluctuations. Fourthly, consider installing surge protection devices on the circuit feeding the electronic ballast to minimize the risk of damage from voltage transients. Further considerations include phase rotation, circuit load, and equipment specifications. Verify the phase sequence is correct, specifically ABC. Ensure the circuit feeding the electronic ballast is not overloaded. Check the specifications of the electronic ballast to determine their voltage tolerance and sensitivity to voltage fluctuations. Detailed troubleshooting steps include firstly verifying the wiring at the junction box as described above. Secondly, testing the voltage regulation of the standby generator. Thirdly, monitoring the voltage at the junction box during the transfer to emergency power. Fourthly, installing surge protection devices on the circuit feeding the electronic ballasts. Fifthly, checking the circuit load and equipment specifications. A more detailed explanation follows. The first area to inspect is the grounding system. According to the 2008 National Electrical Code or NEC, specifically Article 250, grounding and bonding are crucial for electrical safety. The grounding electrode system typically consists of a ground rod, metal water pipe, or concrete encased electrode, all bonded together to form a low impedance path to ground. The standby generator's ground should be connected to this system, ensuring that any fault current has a direct path back to the source, tripping the overcurrent protection device. Connecting the generator ground to the metal junction box could create a potential difference between the box and the grounding electrode system, leading to circulating currents and increasing the risk of electrical shock. Next, consider voltage regulation. Generators are designed to maintain a stable voltage output under varying load conditions. Poor voltage regulation can result in voltage sags or surges, which can damage sensitive electronic equipment. The generator's voltage regulator should be inspected and tested to ensure it is functioning properly. This typically involves using a multimeter to measure the generator's output voltage under different load conditions and comparing the results to the manufacturer's specifications. If the voltage fluctuates excessively, the voltage regulator may need to be adjusted or replaced. Voltage spikes are another potential cause of the issue. Large generators can produce voltage spikes when they are started or when the load is suddenly changed. These spikes can damage electronic ballasts, which are sensitive to voltage transients. To mitigate the risk of voltage spikes, surge protection devices or SPD should be installed on the circuit feeding the electronic ballasts. SPD work by diverting excess voltage to ground, protecting the connected equipment from damage. NEC Article 285 covers surge protection requirements, specifying the types of SPD that are suitable for different applications. Additionally, verify the phase rotation. Incorrect phase rotation can cause motors to run backward and can also damage other electrical equipment. Use a phase rotation meter to verify the phase sequence is correct, specifically ABC. If the phase rotation is incorrect, it can be corrected by swapping any two of the three phase conductors at the generator connection. After that, check the circuit load. An overloaded circuit can cause voltage drops, which can affect the performance of electronic ballasts. Use an ammeter to measure the current draw of the circuit feeding the electronic ballasts and compare the results to the circuit's ampacity. If the circuit is overloaded, reduce the load by removing some of the ballasts or by adding additional circuits. Next, review the equipment specifications. Electronic ballasts have specific voltage tolerance and sensitivity to voltage fluctuations. Check the manufacturer's specifications to determine the acceptable voltage range for the ballast. If the voltage fluctuations exceed the ballast tolerance, the ballast may be damaged. Consider using ballasts with a wider voltage tolerance or installing a constant voltage transformer to regulate the voltage supplied to the ballasts. Now delve deeper into the NEC requirements related to generators. NEC Article 700 covers emergency systems, including generators. This article specifies the requirements for the installation, wiring, and testing of emergency generators. It also requires that emergency generators be equipped with automatic transfer switches or ATS, which automatically switch the load from the normal power source to the generator in the event of a power outage. The ATS should be tested regularly to ensure it is functioning properly. The NEC also provides guidance on sizing generators. The generator must be sized to supply the connected load without overloading. This requires calculating the total load connected to the generator, including lighting, equipment, and other appliances. The generator's output should be sufficient to supply this load with some margin for future expansion. Review NEC Article 440, which covers air conditioning and refrigeration equipment. If the wastewater plant includes air conditioning or refrigeration equipment, these loads must be included when sizing the generator. These loads can be significant and can affect the generator's performance if they are not properly accounted for. Furthermore, review NEC Article 517, which covers healthcare facilities. If the wastewater plant includes healthcare facilities, these facilities must be supplied with emergency power. The NEC specifies the types of loads that must be supplied with emergency power in healthcare facilities, including critical care areas, operating rooms, and emergency rooms. The generator must be sized to supply these loads and must be tested regularly to ensure it is functioning properly. For grounding and bonding, the NEC provides detailed requirements in Article 250. This article specifies the types of grounding electrodes that are permitted, the size of the grounding conductors, and the methods for bonding metal parts. The grounding system must be installed in accordance with the NEC requirements to ensure electrical safety. The grounding electrode system should be connected to the metal junction box and all other metal enclosures using bonding jumpers. The bonding jumpers must be sized in accordance with NEC Table 250.102 cone to ensure they can safely carry fault current. Now, on surge protection, NEC Article 285 provides requirements for SPD. This article specifies the types of SPD that are suitable for different applications, the location where SPD must be installed, and the methods for connecting SPD. SPD should be installed at the service entrance and at any other location where sensitive electronic equipment is connected. The SPD must be listed and labeled for the intended application. Lastly, consider harmonics. Electronic ballasts and other nonlinear loads can produce harmonics, which are distortions of the sinusoidal voltage waveform. Harmonics can cause overheating of electrical equipment, nuisance tripping of circuit breakers, and other problems. To mitigate the effects of harmonics, consider using harmonic filters or reactors. Harmonic filters are designed to reduce the level of harmonics in the electrical system. Reactors are used to limit the current flow of harmonic currents. It is essential to consult with qualified electrical professionals and follow all applicable codes and standards when troubleshooting and repairing electrical systems. This ensures the safety and reliability of the electrical system and protects personnel from electrical hazards. Additional tips include thorough documentation of all troubleshooting steps and findings. This documentation will be helpful for future troubleshooting efforts and for ensuring that the electrical system is properly maintained. Regular maintenance of the generator and associated equipment is also essential. This includes inspecting the generator for wear and tear, testing the generator's output voltage and frequency, and lubricating moving parts. A well-maintained generator is more likely to operate reliably and to provide emergency power when needed. If the problem persists despite these troubleshooting steps, consider consulting with a qualified electrical engineer or generator technician. These professionals have the expertise and equipment necessary to diagnose and repair complex electrical problems. They can also provide guidance on selecting and installing appropriate surge protection devices and harmonic filters. Remember that safety is paramount when working with electrical systems. Always to energize circuits before working on them and use appropriate personal protective equipment or PPE, such as gloves and safety glasses. Follow all applicable safety procedures to prevent electrical shock and other hazards. The proper connection of the grounding system to the grounding electrode system is critical to ensure a safe path for fault current, thereby minimizing risks to both personnel and equipment. Verify that the size of the grounding and bonding conductors meet or exceed the requirements outlined in NEC Table 250.122 and 250.102 CON, respectively, based on the size of the overcurrent protection device protecting the circuit. Furthermore, when selecting surge protection devices, ensure that the SPD voltage protection rating, also known as voltage protection level or VPR, is suitable for the specific voltage and grounding configuration of the system. The SPD should be installed as close as possible to the equipment it is protecting, with short lead lengths to minimize impedance. Evaluate the use of line reactors or isolation transformers to mitigate harmonic distortion. Line reactors can reduce harmonic currents by increasing the impedance of the circuit, while isolation transformers can block harmonic currents from propagating upstream in the electrical system. Perform a power quality analysis to measure the level of harmonic distortion present in the system. A power quality analyzer can measure the total harmonic distortion or THD of the voltage and current waveforms, providing valuable information for identifying and addressing harmonic-related problems. Check the transfer switch operation to ensure it is functioning correctly. Inspect the contacts for signs of wear or damage and verify that the transfer switch is switching the load from the normal power source to the generator without any interruptions or voltage fluctuations. Examine the control wiring of the transfer switch and generator to ensure there are no loose connections or damaged wires. Control wiring problems can cause the transfer switch to malfunction or prevent the generator from starting. Consider using a soft starter for the generator to reduce the inrush current during startup. Soft starters gradually increase the voltage applied to the generator, reducing the mechanical stress on the generator and minimizing voltage dips on the electrical system. Conduct a load bank test on the generator to verify its ability to supply the connected load. A load bank test involves connecting a resistive load to the generator and measuring its output voltage, current frequency, and power factor. This test can help identify any weaknesses in the generator's performance and ensure it is capable of handling the connected load. Additionally, thoroughly inspect all electrical connections in the system, including those at the generator, transfer switch, junction boxes, and distribution panels. Loose or corroded connections can cause voltage drops, overheating, and other problems. Tighten all connections and clean any corroded surfaces. Validate the generator's fuel supply and ensure there is an adequate supply of fuel to run the generator for the required duration. Check the fuel level, fuel quality, and fuel delivery system to ensure they are functioning properly. Implement a preventive maintenance program for the generator and associated equipment. This program should include regular inspections, testing, and maintenance tasks to ensure the electrical system is operating safely and reliably. Keep detailed records of all maintenance activities. Also verify proper ventilation for the generator to prevent overheating. Ensure that the generator room is adequately ventilated and that the generator's cooling system is functioning properly. Overheating can damage the generator and reduce its lifespan. The National Fire Protection Association (NFPA) provides standards and guidelines for the installation and maintenance of emergency generators. NFPA 110 covers emergency and standby power systems, providing requirements for the performance, testing, and maintenance of emergency generators. Consult with a qualified electrical engineer or generator technician to ensure the electrical system complies with all applicable codes and standards. Finally, consult with the manufacturer of the electronic ballasts to determine their recommended surge protection requirements. Some manufacturers may have specific recommendations for surge protection devices that are suitable for their products. Consider using line conditioning equipment to improve the quality of the power supply to the electronic ballasts. Line conditioners can regulate voltage, filter noise, and suppress surges, providing a stable and clean power supply. Remember to consider the environmental conditions in which the electrical equipment is operating. Wastewater plants can be harsh environments with high humidity, corrosive chemicals, and other factors that can affect the performance of electrical equipment. Select equipment that is suitable for these conditions and implement appropriate protective measures. Follow lockout-tagout procedures to ensure the electrical system is energized before performing any maintenance or repairs. Lockout-tagout procedures involve disconnecting the power source and placing a lock and tag on the disconnect switch to prevent accidental re-energization. Check that the circuit feeding the electronic ballast is not sharing a neutral conductor with other circuits. Shared neutral conductors can cause voltage drops and other problems. If a shared neutral conductor is present, separate the circuits or install a dedicated neutral conductor. The location in Portage, Indiana may have specific local electrical codes and regulations that must be followed. Contact the local electrical inspector to obtain information on these requirements. Always prioritize safety and consult with qualified professionals when working on electrical systems.